Good morning students. The first module in NEET crash course class, Electrostatics. So first we will revise important definitions in electric charges and fields as well as electrostatic potential and capacitance, and then we will discuss few important concepts. So first, electrostatics is the branch of physics which deals with the properties of the charges which are at rest. So first, what do you mean by electric charge? Electric charge is an intrinsic property of each and every material object. Because of this property, a material object can exert the force on nearby objects. At the same time, it can experience the force due to the other objects also. So you all know about the important properties of electric charges. So there are two types. One is the positive charge and the other one is negative charge. Like charges are always repels, unlike charges attracts. Electric charges are quantized, they are additive in nature, they are commutative. So these are the few important properties. Next, electrification. The process of charging a body is called as electrification. Insulators can be charged by the method of friction, while the conductors can be charged by the method of conduction as well as induction. Next, the instrument which can be used to detect the presence of charge on a body as well as in order to detect the polarity of charge present on a body is gold leaf electroscope. Next, Coulomb's law, which is also called as Coulomb's inverse square law. The electrostatic force of attraction or repulsion between any two stationary point charges is given by Coulomb's law, and it states that the force of attraction or repulsion between any two stationary point charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between them. It can be written as mathematical form is F is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R square, where epsilon naught is the absolute permittivity of free space. Next concept, effect of dielectric. So dielectrics are nothing but insulators. When a dielectric is placed between two stationary point charges, so the force between them varies. How it varies, that depends upon whether the dielectric is completely filled or partially filled. If the dielectric is completely filled between the two charges, then force between them decreases by k times, where k is the dielectric constant. That is 1 by 4 pi epsilon into k into Q1 Q2 divided by R square. Otherwise, if the dielectric is partially filled, then F is equal to 1 by 4 pi epsilon into Q1 Q2 divided by R minus T plus T root k whole square. Next concept, equilibrium of charge. A charge is said to be in equilibrium if the net force acting on the charge is equal to 0. So there are three types of equilibrium. First one is stable equilibrium. If U is the potential energy, then if d square U divided by dx square is positive, then potential energy is minimum. That condition is called as stable equilibrium. So if the particle is displaced from its equilibrium position, if it comes back to its initial position or equilibrium position, then that type of equilibrium is called as stable equilibrium. Otherwise, if d square U divided by dx square is negative, then U is maximum. That is unstable equilibrium. That means if a particle is displaced from its equilibrium position, if it never comes back to its initial position, then that is called as unstable equilibrium. Next, neutral equilibrium. Neutral equilibrium means d square U divided by dx square is equal to 0. That means potential energy is constant. And when a particle is displaced from its equilibrium position, if it neither moves away nor comes back to the initial position, then it is called as neutral equilibrium. Okay. Next, equilibrium of charges. So in case of similar charges, if two charges Q1 and Q2, they are similar in nature, that means both are of positive type. If they are separated by a distance x, then if a charge Q is placed in between them, a charge Q is said to be in equilibrium if the net force acting on the charge will be equal to 0. That means the force acting on the charge Q due to the Q1 is equal to the force acting on the charge Q due to the Q2. So then the distance to the charge when it is in equilibrium from the charge Q1 is given by x1 is equal to x divided by 1 plus root of Q2 by Q1. x2 is equal to x divided by 1 plus root of q1 by q2. So otherwise, in case of unsimilar charges, that means if one charge is positive and another charge is negative, then the neutral point lies outside the system of two charges. Here charge Q1 is positive while Q2 is negative. In this case, the neutral point N lies outside the system of two charges. Here the magnitude of charge Q2 is less than the magnitude of the charge Q1. The neutral point always lies nearer to the charge having the smaller magnitude. So therefore, the distance to the neutral point from the charge Q2 is given by L is equal to x divided by root of Q1 Q2 divided minus 1. Next, few important definitions. Electric field. Electric field means the space surrounding the charged particle within which electrostatic force can be detected. Next, electric field intensity. The force experienced by the unit positive test charge placed at that point is called as electric field intensity. Next, the electric field at a point near a point charge is given by 1 by 4 pi epsilon naught into Q by R square. Next, neutral point. So in case of electric field also, so the neutral point can be found similar to the force between the two charges. So electric potential, the amount of work done in bringing a unit positive test charge from infinity to that particular point, and more importantly, the work is done against the direction of what? Electric field. That is V is equal to W by Q. This work done is stored in the charged particle as its potential energy. That is W is equal to V into Q or U is equal to V into Q. Electric potential due to an isolated point charge is given by V is equal to 1 by 4 pi epsilon naught into Q by R. Electric potential is positive for a positive charge and it is negative for negative charge. Next, expression for electric field and electric potential due to the various charge distribution. In case of linear charge distribution, that means in case of a straight charged conductor, so electric field are given by the expression Ex and Ey. If the angles alpha is equal to beta, then Ex is equal to 2k lambda divided by r into sin alpha and Ey is equal to 0, where lambda is the linear charge density. Next, in case of a charged circular ring, electric field is given by k into q into x divided by r square plus x square over to the power of 3 by 2. V is equal to kq divided by root of r square plus x square, where r is the radius of the circular ring. Next, in case of infinite sheet of charge, electric field is given by E is equal to sigma by 2 epsilon naught, V is equal to sigma r divided by 2 epsilon naught, where sigma is the surface charge density. Next, in case of a charged conducting sphere, at a point outside the sphere, electric field is given by kq divided by r square and electric potential is given by V is equal to kq by r. If a point lies on the surface, then E is equal to kq by r and V is equal to kq divided by capital R, where capital R is the radius of the sphere. And for the points lies inside the conductor, electric field is equal to 0, but remember the electric potential is constant. Okay students, next the concept of electric field lines. So electric field lines are imaginary lines drawn just to represent the electric field in a figure. So you all know about the important properties of field lines. Electric field lines always starts from a positive charge and terminates on negative charge. Two field lines never intersects with each other and the field lines are always normal to the surface of the conductor. So next, equipotential surface. So it is an alternative method for representation of electric field. Equipotential surface means the surface at where the electric potential is same at each and every point. Important properties. Two equipotential surfaces never intersects with each other. The work done on moving a charge on an equipotential surface is always equal to 0. Next, there is a relation between electric field and electric potential. Electric field at a point is numerically equal to negative potential gradient, that is E is equal to minus dV divided by dr. Next, in order to assemble the system of two charges, work has to be done. That work done is stored in the system as potential energy. The potential energy of system of two charges is given by U is equal to 1 by 4 pi epsilon into Q1 Q2 divided by R. In case of system of three charges, the potential energy is given by 1 by 4 pi epsilon into Q1 Q2 by R12 plus Q2 Q3 divided by R13 R23 plus Q3 Q1 divided by R31. Next, electric dipole. It is a system consisting of two equivalent unlike charges separated by a certain distance. Next, electric dipole moment. Electric dipole moment is a vector quantity and it is measured as the product of the magnitude of either charges and the distance of separation between them. Electric dipole moment is always directed from negative charge to the positive charge. Next, electric field due to the electric dipole. At an axial point, electric field due to the dipole is given by 1 by 4 pi epsilon into 2 pi by r cube. Equatorial line, E is equal to Kp divided by r cube, and at any general point, E is equal to Kp by r cube into root of 3 cos square theta plus 1. When an electric dipole is placed in the external electric field, it experiences the torque which is given by tau is equal to P sin theta. Because of this torque, the electric dipole gets rotated. The work done required in order to change the orientation of electric dipole is given by W is equal to Pe into 1 minus cos theta. This work done is stored in the dipole as its potential energy, that is given by U is equal to minus Pe cos theta. Okay students, next, equilibrium of electric dipole when it is placed in the external electric field. So the electric dipole is said to be in stable equilibrium if P and E, that means the direction of electric dipole moment and the electric field are same. That means theta is equal to 0 degree, then torque is equal to 0, work done is equal to 0, and potential energy is minimum, that is equal to minus P. That is the condition for stable equilibrium. Next, the electric dipole is said to be in unstable equilibrium if P is perpendicular to E. Theta is equal to 90 degree, tau is equal to Pe, work done is equal to P, and U is equal to 0. So the electric dipole is said to be in neutral equilibrium if P and E are anti-parallel. That is, theta is equal to 180 degree, tau is equal to 0, work done is equal to 2 Pe, and potential energy is maximum, that is equal to P. Next, electric flux. The total number of electric field lines passing through unit area where the surface being held perpendicular to the direction of electric field. The mathematical form of electric flux is given by phi is equal to summation of EDS cos theta. Next, Gauss law. Gauss law in electrostatics states that the total electric flux through any closed surface is always equal to 1 by epsilon naught times the total charge enclosed by the surface. That is, phi is equal to 1 by epsilon naught times the total charge. Capacitance of a conductor is its ability to store the charges, and that is given by C is equal to Q by V. That is the ratio of charge added to the conductor to rise in its potential. So capacitor is a device which is used to store the electrical charges. There are different types of capacitors. First one is parallel plate capacitor. So in case of parallel plate capacitor, capacitance is given by C is equal to epsilon naught A by D in the absence of dielectric. When a dielectric is placed between the two plates of the capacitor, then its capacitance increased by K times, that is C is equal to epsilon naught Ka divided by D, where A is the area of the plates and D is the distance of separation between the two plates. Next, spherical capacitor, its capacitance is given by C is equal to 4 pi epsilon naught into AP divided by B minus A. And cylindrical capacitor, its capacitance is given by C is equal to 2 pi epsilon naught into L divided by log of P by A to the base E. Okay, next, charging of a capacitor. During the charging of a capacitor, energy will be stored. So energy stored across the capacitor is given by U is equal to half CV square. Next, dielectrics. Dielectrics are the insulating materials where they do not have any free charge carriers. Next, in dielectrics there are two types. One is polar dielectric and another one is non-polar dielectric. Next, properties of dielectrics are in electric field. So when a dielectric is placed in between the plates of the capacitor, the capacitance will get changed. So when in that case there are two conditions. In case when the battery is connected and the battery is not connected. So in the first case, when the battery is not connected, the capacitance will be increased by K times. The charge remains same, charge will be conserved. Potential is given by V dash by V by K, V dash is equal to V by K, electric field is given by E dash is equal to E by K, and the energy stored is U dash is equal to U by K. Next, across the capacitor, if a battery is connected, then capacitance will be increased by K times. Charge, new charge, Q dash is equal to K times Q. Since battery is connected, V dash is equal to V only. Battery maintains the potential difference between the plates. E dash is equal to E by K, and U dash is equal to K times the initial energy stored. Next, in case of parallel plate capacitor, when a dielectric is placed, so capacitance will be increased by K times. So that depends when the dielectric is fully inserted or partially inserted. So in case when a dielectric is completely fully inserted between the two plates, capacitance is K times epsilon naught A by D. When it is partially inserted between the two plates, then C dash is equal to epsilon naught A divided by D minus T plus T by K, where T is the thickness of the stab.